Hi everyone, my name is Valery and I'm a CTO at company F3. F3 is a Latvian startup, a social network with more than 25 million users worldwide. This talk will be about building microservices using GRPC, our experience with it in F3. I will give a quick overview of GRPC, what it offers to developers, talk about composability, and finally bring up some topics in fault tolerance and resilience that are crucial for production environments. So GRPC is a framework from Google, which was used by them internally before it went open source in 2015. Its job is to make efficient communication between services with pluggable support of various aspects, like load balancing, discovery, health checking, and a few more. We started to work on F3 in 2017, and we are heavy users of gRPC ever since. Key features of gRPC are high performance and efficiency, which makes it ideal for low latency, highly scalable distributed systems. It facilitates protocol and domain model design by giving a way to write strict specifications, which are language independent. gRPC is leveraging HTTP2 or a second version of HTTP protocol for its communication. What makes it possible for clients, for example, mobile devices, to connect directly to gRPC services. Finally, gRPC is designed for easy extension with plugins. So under its hood, gRPC is using protocol buffers, which is a Google open source mechanism for serializing structured data. Probably many of you heard about it. It was open sourced in 2008. Key benefits for developers are code generation, which reduces boilerplate code that usually needs to be written. Out of the box, Protobuf, at least for Java, generates builders for all objects, which are immutable and null safe. Since all code is type safe, it's hard to make mistakes because compiler will always throw errors at you. It is refactoring friendly, meaning you can rename fields, which is much harder with JSON. And finally, Protobuf supports most popular languages out of the box. You can serialize object in Java, for example, and deserialize it in Go without any issues in a type-safe manner. So on the slide, you can see I have a simple message person with ID, name, and email, and builder, which creates this person, which is immutable and null safe. Null safe meaning that if you will type person, new builder, and just build without anything, it will have default values for all fields, like 0 for numbers, empty string for string, and etc. So I will have to give you a simple example of gRPC service in order to show you its features. So please bear with me. So here we have a person service, which has defined one method getPerson. It takes getPerson request and returns getPerson response. This request contains a person ID, and a person is a message that we've seen here on this slide. So simple service implementation looks like this. We extend the implementation base class, override service method. Here I created a very trivial hard-coded implementation. gRPC is using stream observer interface, which kind of resembles reactive style on next, on error, and on completed methods. Code needed to start server is very simple. We specify port, add needed services, and basically just start it. Very simple. And this is how the output looks like. It resembles JSON. So protocol buffers can print out in a way like this. Okay, one moment. Oh, sorry. I missed the slide. So this is a blocking client. So this is a way how to work with our started service. So basically, we specify host name and port. We specify that we are creating a blocking client. We create request and basically invoke the service method on the stop. And we can see that the output resembles JSON because protobufs, you can print it out like a JSON. To simplify reasoning about services, we can think about them as models, and their methods can be thought about as functions in those models. Any call to service method can be thought about functions that take service stop with request parameters and arguments and returns desired result in a function return type. We will get back to this topic in future, but for now, let's see what other gRPC clients we have. So we have a feature client, which is a synchronous way to call the service. It offers Java features interface, and we probably all know how to work with it. So let's go to the next one, which is Async client. This is how they call it, and basically it resembles a reactive approach where we have on next, on error, and on completed methods. So code here gets a little bit hairy because we have to define the stream observer object. And I also had to use finish latch here because in order to this code work and not exit upon launch because it's all asynchronous. So I will have to tell you a big secret. There is a great API design guide from Google. It is not big, but it is very. It contains a lot of important informations like naming conventions, design patterns, how to organize your code, how to handle exceptions, and many more. When we started to work with gRPC, there was no such guide, and we were pretty happy to discover that many of solutions we used, they kind of resemble the solutions that later we found in this guide, and we're trying to follow it very closely. So adding more services is very simple. You just add it in server builder. Usually it will involve some kind of dependency injection. Probably you will resolve all your service dependency graph and put it here using your favorite dependency injection frameworks. And basically that's it. A couple words about discovery and load balancing. Since gRPC offers pluggable model, we can write and specify our own discovery and load balancing policies. In a free, we're actually just using a simple out-of-the-box round robin and a customized service for discovery using Zookeeper. Basically, each service after start registers itself in service registry and gets into round robin rotation. If it fails or for whatever reason is not healthy, he will be kicked out of service registry and kicked out of rotation. So how do you run the server? Usually for launching and running, there are numerous options since it's a simple Java application, or if you're using other languages, code will be similarly simple. We can easily launch it at localhost. All services will be run in a single server on localhost. For testing, we can use Docker or Docker Compose. For actual environments like development and production, we would use Kubernetes or whatever actually you prefer. Some services that are specialized or require a lot of resources can be started separately, since you define all the services on which can be run on this server. In a free, we have a couple of such. For example, one is for text moderation, which has a lot of patterns. It loads them in memory and creates a specialized data structure for quick pattern matching in text. And in order to not to interfere with other services, we start them separately and run as a separate instances. So there are a couple of questions. So how do we organize our services? Is it just a simple divide and conquer? For the most part, yes. Most of services are simple CRUD-like functionalities that follow conventions and guidelines. But for use, usually it is not so simple, and it requires some complex logic and probably information from many other services. And we call such services as facade services. This is our way of doing it. It is not mandated by Google or written in GRPC guidelines. This is what we found works best for us, and maybe you can find a better way yourself. So, for example, getting user profile information usually will involve checking authentication credentials, anti-abuse counters, blocks, something else, and only then getting user information from the actual user service. Those interconnections can get messy very quickly, but we have a tool to manage complexity, and we will get into it soon. For now, remember that we treat service methods as simple functions. There is one more design decision to make. If we are making mobile backend, we have 3 options with gRPC. For example, mobile devices usually communicate with server using REST API. It is simple and convenient, easy to test and understand. We can just add this layer on top of gRPC, but usually it involves writing a lot of boilerplate code, but this is how it is. Second option is transcoding gRPC into JSON and vice versa. Basically, you can communicate directly with gRPC server using JSON, which is generated from service proto specification. It has some limitation, but this involves less boilerplate, and you, in the end, still have a REST API. But you have to use a proxy in front of gRPC to get this transcoding right. The third option is going gRPC native, meaning clients will communicate directly with gRPC services using Protobuf messages and HTTP2 connection. This is more efficient and faster, but goes away from REST API, which may not be convenient and easy to understand in some cases. I run quick numbers for you to give some perspective on how we in F3 are using gRPC. At the moment, we have around 80 services and about 1,000 service methods. Usually we navigate in code by alphabet and conventions. It's too much to keep in head. We have 4 facade services. One is API, which is closely resembles REST API used by mobile devices for communication. Upload API, which is used for uploads and resumable uploads. Admin API is used for our internal admin tool, which is basically a separate app. And Dev API, which is used by our internal tools and testers. It is super convenient to have separate Dev API and admin API. We also have command line tools that use gRPC to make some migration or data fixes. They connect directly to gRPC services. And it is very useful to make some data fixes or migration. One drawback with gRPC is that it involves code generation, and if you change something, you have to regenerate code. And if your project is big, probably it can take, it can be annoying to run this generation every time. And also generated code can take quite a lot of space. For example, for us, compiled generated code takes about 25 megabytes, which is around 1/5 or 20% of our whole application. We can tweak Protobuf to get it smaller, like in even 1 megabyte, but then we lose immutable objects and builders. Our philosophy is to leverage compiler as much as possible. If we can make it do extra work, namely checking code and ensuring there are no bugs, we will likely do it. Compile time protection is like having automatic unit tests that fail compilation if they do not pass. We're using separate REST layer. Back then it was too risky to go with gRPC native approach, and there was no gRPC transcoding. Now we would probably go with gRPC native approach. It simplifies communication and many other aspects. For example, versioning. In some cases, for example, when you rename fields, you would need to roll a new REST API version for the method, but it would have not been required with gRPC. Also, we have some ability to make some small tweaks on REST layer, but we try to do it minimally. So after reading Google API Design Guide, we decided to enrich our person service with more methods. There are some conventions or design patterns which typically involve batch get, create, delete, get, list, and update methods. So in batch get, you basically pass some IDs and get those objects in response. Create a method usually will take necessary fields for the object and return newly created object. Delete will take an ID and basically return nothing. And in Protobuf, there is a design pattern or recommendations that if you have such method, you return Google Protobuf empty message. Get, our familiar get object will take an ID and return the object. There is also variation of get that involves getting all the objects, and list will involve pagination. Say if you have, you will pass paging request with limits, offsets, or cursors, maybe some query, and you will get a paged result back with paging response and those objects. And update will take updated object, a field mask, which basically tells what fields to update, and in response you will get updated object. I would also I forgot to mention that, for example, get persons, take one request, get person request, and returns a stream of responses back. Basically, if you would like to get all persons, they may not fit in one response because, for example, if you have millions of them, then you would return them in chunks, and stream means that you have a stream of responses. So, for example, if you have 10,000 persons, and you can get one response with 10,000 persons, and if you have 20,000 persons, you can get two responses with 10,000 in each. So here we have 4 different types, which I would like to discuss. So the first one is very simple. It's like one request, one response. Second one is one request and no response. Third one is collections. Basically, you pass one request and get a few responses back. And second one, and the last one is not supported out of the box in gRPC, but still it's very useful to think about it. It is an optional. So, for example, if you pass a person, get person request with IDs that does not exist, you will get an empty response. Or if this ID exists, then you will get an actual get person response. Without it, you would have to return either an error or some empty object or something to indicate that there is no response. But it is very useful to have this distinction from actual values, that you have an optional that can be empty. So those are 4 basic blocks of 4 basic types that we need our service to have. So in order for us to get there, remember that we are treating methods as functions, and we can leverage RxJava to give us convenient types. So basically, there are single completable, observable, and maybe interfaces out of the box in RxJava, which basically map to these different types our services return. And remember that each call to the service is like an asynchronous operation that will take some time. And working with such asynchronous jobs is exactly where the power of reactive framework lies. Since this is not an Rx masterclass, I will not dive deep into it. I will just summarize it here. So basically for this service definition, we have these functions and their return types, which you can see. Basically, it's all mapped to single completable, maybe and observable types. Why would you need it, you might ask, because what's the point of going this far and basically making an Rx reactive interface of gRPC? And I would like to, and I think that it is composability, and I think that composability is like an essence of programming. This is why programming is so useful. We can combine small blocks of code into larger blocks of code that do something useful. We have expressions, statements, control flow structures that we can mix and combine. Out of the box, it works really well with blocking calls. It gets trickier with asynchronous calls, which are usually not composable. For example, one attempt to deal with asynchronous calls with callbacks can lead to callback hell and many other interesting places. And the cleanest and most powerful way of dealing with such asynchronous calls so far was offered by functional reactive programming. It is type safe, at least in Java. It is fast and leads to compact code. We can think about Lego blocks here that easy snap and combine together. I was thinking quite a lot about what example to give you here, because it should be something really simple and hopefully make a click in your head. So please bear with me. So Java out of the box have 3 composable classes. I will tell you one of it, and the other 2 you can think about. Maybe you know them, and we will get to it later. So optional in Java is composable. Let's look at it. In this example, we would like to concatenate two person names if they both are present and get optional as a result. In a straightforward approach, using just get will get you an exception at runtime. The second attempt using is present checks will avoid exception, but still you will not have an optional as a result. Of course, you can wrap it as an optional, but basically you hacked it apart and then assembled it together, and this is not the way how it was meant to be used, how an optional was meant to be used. Proper way of doing this is by using flat map method of optional. And yes, it is not, it is an original Java optional method and not something to do with RxJava. But optional in Java is a little bit messy and it lacks many convenience methods. So let's look at similar code using maybe. So here at first line, we have actual service call, and remember that we treat them as functions. And the second maybe is just, for example, empty. So maybe have a zip method, which basically you pass a block of maybes, and the functions that will be executed if those maybes are present. Similarly, we can write our own zip method for optional. It's very similar. It's said that it is not present in out of the box in Java. And I would also encourage you to try write similar code with using free optionals, and you will find that it is something quite tricky to do. So also we can go from optional to value by, for example, doing or else, calling or else method. And similarly, we can go from maybe to single by providing the default value, which is basically the same. And you can see how optional and maybe are related basically one-to-one. So why do we need composability? The answer is to manage complexity. Building logic from small gRPC service methods will now be as simple as assembling some Lego blocks together, easy to snap and fit together. We actually can get pretty far on that and implement pretty complex and challenging business logic with those four types. It is also type safe, which leads to less bugs and reduces complexity by not having extra ifs, callbacks, or other structures or hacks that people tend to use. We ended up using Rx almost everywhere where we have asynchronous jobs, and it's practically everywhere. All storage layers, network layers, manipulation with disk, calling external utilities like image manipulations, all those four basic building blocks are asynchronous and help us to make all this work together. I have to mention that there are alternatives. We are not like, there are a lot of interesting frameworks. I do have some experience with Spring Reactor, but their issue is that they have only two building blocks. It's like Mono and Flux. And the issue is that Mono is basically a single, maybe, and a completable in one type, and it is not convenient and type safe to use it. But of course, you can write a little extra code and get those four types in Spring Reactor as well. There are, I think, Kotlin Flow and many more libraries probably I'm not aware of, but still, the main goal is to get the composability and not a specific library. Finally, we're getting to fault tolerance and resilience. Those topics are very important for production. Quick note about difference between those two. So we say that system is fault tolerant if, sorry. So we say the system is fault tolerant if in event of failure, it can fail over and perform function without user noticing a failure. So basically it's transparent. And we say that system is resilient if failure can be observed by some users, but system continues to function normally for others. So only part of users can notice it. There are a few frameworks for that. I will just quickly talk about those I had experience with. Initially, we used Hystrix, and we used it in previous project, and for a long time, it was good, but it got obsolete, and it is not maintained anymore, and it served as a pioneer in those resilience patterns. Later, we switched to resilience for J. It is targeted for more modern Java versions, more lightweight, and works really well with functions. Amazing framework. And let's quickly go through some of the most common patterns that are used in fault tolerance. Basically, they're summarized in the table, and I think we use all of them in F3. Retry is used to repeat failed executions, circuit breakers to reduce number of errors, rate and time limiters as well as bulkheads to limit concurrent executions. Cache is obviously for caching, and fallbacks are alternative results in case of failure. I will not dive too deep in this topic. You can search it for yourself. But as a quick example, I will explain a circuit breaker. Its name comes from a real electrical device, which probably most of you have in your flat or house in the electric panel. So this is mine. And basically, a circuit breaker is an electromechanical switch that, when tripped, will cut off electricity to section of wires that it is protecting. Its job is to protect electrical wire from overheating in case of overload or short circuit. Without such protection, in case of failure, wire usually gets red hot and causes much serious problems. In case of programming, a circuit breaker pattern job is to protect infrastructure from being overwhelmed by failures. For example, if one service method will start throwing errors and the error rate will reach a certain threshold, circuit breaker will become open, and for some time, all calls to the service method will instantly return exception like, sorry, circuit breaker is open. After some configurable period of time, circuit breaker will close and allow calling service method again. As a bonus, usually such frameworks come with tools to collect statistics. Those are execution numbers, successes, failures, average latencies, timeouts, retries, and etc. We can build charts and monitoring tools using the data. Needless to say that this is a must for monitoring and DevOps in production. Speaking about resilience in a free, so basically we have limits everywhere by setting some default value for all the methods and overriding some of them for ad hoc methods. We can do it all at the runtime. It takes some time to figure those numbers. And we have sophisticated system for preventing system abuse from bots and scripts. But if it fails or there is a new way to abuse the system, rate limiters and bulkheads can help you to mitigate the damage. And sometimes we're not perfect and commit some mistakes, like calling server too frequently from clients and or having faulty logic in some service method, and we can quickly detect that. Lastly, we use it as a part of system monitoring, which saved us many times. So for summary, I would like to highlight that gRPC is a simple and robust framework for making microservices. I would like to thank Google for making such a framework and sharing it with us. Also, making API design guidelines takes a lot of experience and effort, yet we have it all for free. In a world of microservices, we can live by making small methods and safely composing them into more complicated services and methods using frameworks like RxJava. Resilience can be achieved relatively easy by decorating all service methods using some common resilience patterns. And finally, I would like to say that all those frameworks on their own are like marvels of technology and years of experience. But combining them together into one system makes things truly shine. We have virtually no problems with our microservices setup in a free. We have only 2 backend developers and 1 DevOps to rule it all. And I would like to thank all the developers who made those frameworks. So going back to the free composable classes of Java, if you figured it out, you can write it in chat. And basically, this is the end of my presentation, and thank you all for watching. So I will go back to the chat.
Can you hear me?
Yes, I can hear you.
Oh, no bug this time. That's nice.
Okay.
Yeah. So yeah, if you have questions, please ask them now or be silent forever.
Okay.
So from your presentation, I figured out what's the name of the thing I have to fix. It's called Circus Breaker.
Okay, Nikita, you got it right. Yeah, easy one. You can send your CV to us. We can talk about it.
Okay, while we are waiting for questions, I will drop the link where people can leave feedback for your talk.
We have, so how many employees do we have We have around 25 people, and about 12 of them are related to technical team. So 2 backend developers, 2 iOS developers, 2 Android developers. That's 6. 1 DevOps, 1 web, and 4 testers. Yes, there are some challenges with gRPC. Basically, in the beginning, we had to write some boilerplate to get reactive interfaces work. But luckily, Salesforce guys wrote a plugin that for gRPC that generates all this necessary code. So probably the only issue with gRPC is getting that code generated so that you would not have to write it as a boilerplate. How do you deal with Rx? Do you check that you are not blocking event loop? Actually, we have 0 problems with Rx, and we are not even switching threads or something. We think are staying on gRPC threads, and there are no issues with that. Okay.
I will rewrite, otherwise people are afraid to give feedback on your talk.
Okay.
Hopefully now we will get all 64 giving us the number.
Okay.
So for those who are wondering, can you buy Circus Breaker now with code restrictions? Yes, it's possible. I have time till 21 o'clock to go to depot.
Do you plan to try other JVM languages in your backend apart from Java? Well, actually, we're using Kotlin. I think 1/3 of our services are written in Kotlin, and there are virtually no problems with Kotlin. It's just the code is more compact. It's all works just fine, and we tried it, and it works also fine. So we use Kotlin and Java. For command line tools, I think we're using Go, and you can literally write any client in any language for your gRPC services.
We can wait for like 2 more minutes if there show up more questions. Meanwhile, most important stuff what we have to what's left for tonight. You also get
Okay, yeah, piece of code.
result of Latvian berries and socks, definitely.
Okay.
Yeah, if it will go longer with restrictions, maybe we should switch to underwear as well, and chocolate for
Okay.
you as well.
Okay, thank you.
So
Thank
it's a
you.
question, right?
Okay, we haven't tried Kotlin Flow. Maybe we should, but I'm not sure that they have those 4 basic building blocks that we heavily rely on. Probably we can easily achieve it, but yes, probably we can look into it. So how do you deal with slow non-facade microservice, which is not failing, but slowing things down below the rate of coming to facades? Well, it depends on how much it is slowing. So you will have some time limiters which will fail if it is really slow. If it is like on the border values, then of course system will get slower. But usually you set those limits to reasonable numbers, and it should work pretty well. And usually you will get alerts about the performance degradation, and you should take a look into it with your DevOps team. Occasionally we have some of that, and usually we have health and liveliness probe checkers in Kubernetes that will notice it, and if it's like really slow, it will kill it and restart. So for some time, for some period of time, you will have some performance degradation, but it will recover after some time. We had some issues like that at night when something went out of control, but it recovered after, I don't know, 10 minutes of degraded performance. Manually, are those limit numbers determined manually or automatically? We set reasonable numbers, usually like very high numbers that are impossible for normal people to achieve, only if they start writing scripts or using some bots. And yes, basically it involves some trial and error. Usually if you set it a little bit lower, then you will get some errors. Then you can decide that, okay, it's like a valid use case and you can increase it. And we have some limits, for 1 minute, 10 minutes, 1 hour, and 1 day. So you play with numbers, but basically, yes, it's kind of manually. But yes, if it would be automatic or some adjustable, it probably would have been better. But it involves making such system. Usual requests per second at facades. I think it has something to do with thousands per second. Maybe 1,000 per second is a good number. And so basically we have 16 machines, and they all have like all the services running except for text and a few others, which are like separate servers. And it is in auto scaling group. So if the CPU is if CPU gets high, it will add another node. If it gets low, it will go to the minimum amount of servers. And but basically we have like 1,000 per second requests with 16 machines, which basically are like 4 core, 4 gigs machines.
So I assume there are no questions anymore right now. So if people want to ask you a question, how they can reach you?
They can write it on my email. You can see it in presentation. I'm not sure. Should I write it in chat also?
You can write it, yeah.
Okay. So answering to Oleg's question, yes, Oleg, but you're speaking about only one method. There are like 1,000 of them. But okay, facade maybe have about 200 of them. So yes, maybe it's, I don't know, 300 requests per machine per second. Yes, maybe. But since we're running it in Kubernetes clusters, and on those 16 machines, we also have stream nodes that are doing Kafka processing. We also have REST API nodes. We also have upload nodes, and they all share the same machine, and they are all in the same auto-scaling group. But we have like no problems with that. And performance-wise, we also have no problems since mostly latencies are coming from network, but not from our internal network lag or latency. And the previous question was about slowdown of CPUs, but due to disks, networks, etc. Well, actually, we never had this problem. If network fails, it actually fails pretty hard, and the node just goes down, or the service gets thrown out of the rotation because health checks are not working. And disks. Speaking about disks, we actually I think all the things that are interfacing with gRPC are in memory, so we're using Redis, and there are actually no disks involved on this route with gRPC. So we actually never had this problem.
I suggest that we finish now, and everybody who gets any new question, please write to Valery's email. And thank you very much for your story. Once